So sometimes we're wanting to know a qualitative characteristic as opposed to a quantitative. So we're going to look at the proportion of successes in a population, where remember a success is just whatever particular outcome we're looking for. So in this case, in the example of the cars, the ultra green cars, we were looking as a success as they get over 100 miles per gallon, right? So what is the proportion of the population that gets over 100 miles per gallon? Well, again, we don't know the population parameter, but we can calculate the sample proportion and use that as a point estimator. Now remember, the central limit theorem says that for proportions, for means, we just said we needed a sample size usually of greater than 30. But for proportions, in order to assume that it's a normally distributed sample, we have to have sufficiently large sample sizes, which we defined as n times p, so the sample size times the probability is greater than 5, and n times 1 minus p is also greater than 5. So again, we're going to have to check to make sure that these are normally distributed, or that we can assume they're normally distributed before we can use these formulas. So again, with our confidence interval, which we're defining as alpha as our margin of error, so 1 minus our margin of error gives us our confidence interval. We're going to go back to those z-scores, where we're going to look at p bar, which is the sample proportion, plus or minus the z-score multiplied by the square root of the whole thing of the sample proportion times 1 minus the sample proportion divided by n. Okay, so again, we got to make sure we're following our orders of operations, and this formula should look familiar because we've looked at this before. We haven't exactly calculated a confidence interval, but we've looked at this before in an earlier chapter when we were talking about proportions and z-scores and those sorts of things. So let's go back to our example with the green cars. We want to estimate the proportion that the ultra green cars obtain over 100 miles per gallon, because that was the claim made by the manufacturer. And so using a 90% confidence interval, we're going to construct that, a 90% level of confidence, we're going to construct that confidence interval. Now, we're told here that the normality assumption is met since n times p is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5, where the population proportion is 0.28. But we're going to go ahead and test that out. Okay. So let's jump over to Excel. We're going to be back in that MPV worksheet there, but let's jump over there. So I've still got all of my data up from video 2, where we were calculating those confidence intervals. So we can delete that, or you can leave it on there and just move over a little bit. I'm going to just go ahead and delete it so that we're not confusing. Now the first thing that I want to do is let's calculate the number of successes in this sample. So remember, a success is getting over 100 miles per gallon, okay, or greater than 100 miles per gallon. Now we can go through, since there's only 25, we could go through and manually count those, or we could use an Excel formula to count them. So let's use an Excel formula. So we're going to define this as number of successes, and we're going to use the formula of count if. So this is telling us it's going to count the number of cells that meet our criteria. So our range is A2 through A26, which is where all of our data is, and our criteria, and here you have to be specific, you want to put this in parentheses, is greater than 100. Okay. Now, if we want greater than or equal to 100, we would say greater than 99, right? Or greater than or equal to 100 there. But we're going to say greater than 100, get over 100 miles per gallon, because that was the claim of the manufacturer. And so it tells us that 7 out of the 25 cars in our sample got over 100 miles per gallon. So then we can calculate the sample proportion, or what we'll call P bar. as the number of successes divided by the sample size of 25. So remember, n is our 25, n is our sample size. So our p-bar for this formula is 0.28. Now let's go ahead and test based on this data to see if we can assume that this is normally distributed. So NP, first of all, is going to be equal to n is our sample size, and I don't have that up here, I'm just typing it in, times our proportion of p here is 7, which that is greater than 25. And then n times 1 minus p is going to be equal to 25 times, open my parentheses, 1 minus p bar, our sample proportion here is 18, and that is greater than 5 also. So again, we're good there, but we just wanted to test that out. Okay. So remember, we're looking at a 95%, was it 95? Oh, sorry, a 90% confidence interval. And so with a 90% confidence interval, that means we're looking at 5% in each tail. Now, we can know, just because we know that the z-score is 1.645. We can look that up in the table. We've probably written that on our notes, and so I know, all right, 90% confidence means there's 5% in each tail, and that's a 1.645 z-score. Right? But just in case we had forgotten how to do that, or we didn't have our formulas, our tables with us, or maybe we just we forgot, or it's an odd number, let's go ahead and refresh our memory on how to calculate that z-score. So remember that z-score we calculated in an earlier chapter. We're going to use the norm.inverse formula. Okay, and so our probability, so if we're looking at 90% confidence interval, that means there's 5% in each tails. Well, remember, this is calculating the right tail, so it's looking at what's the probability that everything to the left of that right tail, so it's 1 minus the 5%, or 0.95. And then our mean, oh, sorry, I gave you the wrong, norm.s.inverse. I was like, wait, why is it not working? So 0.95. And so there we get our z-score of 1.645, or it runs a little farther out. So let me go back up here. It's norm.s.inverse. I typed the wrong formula in. See how easy that is to do, especially when so many of the formulas look the same and just have maybe one little bitty tiny difference. It's very, very easy to get confused and use the wrong formula. So it's super important that you take good notes and that you've got your formula sheet all printed out. I have my formula sheet sitting right here next to me, and I just read the formula wrong. All right, so my confidence interval then is going to be, and I'm going to go the upper limit and then the lower limit, or the upper and the lower, is going to be equal to, remember, my p-bar, my sample proportion of 0.28. I'm going to say plus because I'm calculating the upper. My z-score, which I've already got right here, although we could embed that formula in this, multiplied by the square root of, and then I've got to, this is where you've got to be really careful with your parentheses and make sure that you're getting those all in there correctly. So it's the square root of everything. So remember, the numerator then is the sample proportion multiplied by 1 minus the sample proportion, close two sets of parentheses there, divided by the n, or the sample size, which is 25, and then close my last parenthesis, and I get 0.427, 707, blah, blah, blah. And then for my lower limit, again, I'm just going to go through here and make all of these, F4, make all of these be absolute values so that I can drag it down. All right. So I'm going to drag it down, and I'm going to change my plus sign to a minus sign. All right, so I've dragged my formula down, I've changed the plus sign to a minus sign there, and so then my lower limit is 0.13. Now again, we can change these to percents if we want to make it a little easier to discuss. So I'm going to highlight those. I'm going to hit the percent sign here under the home, and let's add a couple of decimals. So we can say that with 90% confidence, the proportion of the percentage of cars that will get over 100 miles per gallon is 42%, falls between 13.2 and 42.8%. Okay. So that's with 90% confidence. Now let's say that we wanted 99% confidence. Well, the only thing that we would have to change to get 99% confidence would be our Z-score, right? So our Z-score for 90, this is for 90% confidence. I'm going to type that up here, 90% confidence. Let's go over here and make 99% confidence. Now again, we can just type in our Z-score if we want to, or we can just change our formula here. So at 99% confidence, that means there's 0.5% in each tail. So this would be 0.995, which gives us our Z-score of 2.576, rounded roughly. And now I can just drag these formulas over. Now I'm going to have to do a little adjustment here because I don't want it to reference cell D6. I want it to reference cell E6. So I'm going to go back up here and change this one thing in both formulas because I want it to reference my new Z-score, my 99% confident Z-score. So I can say with 99% confidence that the probability that a car will get over 100 miles per gallon is between 4.9 and 51.1. So notice that the more confidence you have, the wider your confidence interval is.